everyone. Just wait a minute to see if anyone, okay, yeah, we got one more waiting to enter. Okay. All right, this next week's lab is called 1-bromobutane, and it is in the Williamson hardcover textbook. Okay, so 1-bromobutane. Okay, I'm going to share my screen. And let's see, we've got some others that are waiting to join. Just a minute here. Okay. Okay, you should be able to see my screen. Okay, last time I showed you the cover art for this article, When Drug Molecules Look in the Mirror. I'm going to go over just a few of these. Over. Okay, one example of a compound that has different biological activities for its enantiomers is amphetamine, and the S plus isomer is 3 to 4 times more potent than the R minus. The R minus also produces adverse cardiovascular effects. I don't think amphetamine is used as much as it used to. It's also called dexedrine. It's used to treat hyperactivity, ADHD, and also sleep disorders like narcolepsy. All right, the next one is L-DOPA. Okay, only one of these enantiomers is useful in treating Parkinson's disease. Okay, the other isomer contributes to side effects. Okay, notice also here that in past lectures, we were talking about R and S and plus and minus. You can see there's no simple relationship. There are some S isomers that have a plus rotation of light, some that have a minus, but the R isomer will have the opposite. All right, the next one is, okay, we'll talk about ibuprofen, the main ingredient in Advil and Motrin. Okay, analgesic activity resides primarily in the S plus. The body does racemize ibuprofen. So it's not necessarily economically feasible to make exclusively the S plus isomer. Right, ketamine is an anesthetic. Okay, the S is more potent, the R produces side effects. Okay, here's another example. This one is used in treating hypertension, while the enantiomer contributes to side effects. Right. Penicillamine is used to treat copper poisoning. I wondered about that. How do you get copper poisoning? There's a rare condition called Wilson's disease, in which copper accumulates in the body, and one of the symptoms is a golden yellow ring around the iris of the eye. Tetramycin is used to treat parasitic infections. Okay, and again, one enantiomer is beneficial, the other one produces undesirable side effects. All right, thyroxine. Okay, this is an example where the two enantiomers both have beneficial effects, but they're different effects. Thyroxine is prescribed for thyroid deficiency. Okay, notice the iodine atoms here on the benzene ring. The R plus is used to decrease serum cholesterol. Timolol, this is another example where the two isomers have different biological effects, in fact, and they're used for different purposes. This belongs to a class of drugs called beta blockers. The S minus is prescribed for angina and high blood pressure. The R plus is prescribed for glaucoma. And then the last one, warfarin, this is a blood thinner, an anticoagulant. The S minus is more potent and it's also eliminated more rapidly. Okay, so we can have all sorts of different situations. One isomer can be harmful, the other one can be beneficial. One isomer may not do anything. They may have similar effects, but one isomer is more potent. And both isomers may be beneficial, but they have different biological effects. Oftentimes in natural products, just one enantiomer occurs in nature, and if both enantiomers occur in nature, they're often not from the same source. We saw that last time with the carvone. One enantiomer is found in spearmint, the other is in caraway, two completely different plants. Okay, this example of a single enantiomer in nature came to light several years ago in Oklahoma. The law enforcement agency seized a white powder, took it to lab and isolated it, and it turned out to be racemic cocaine. And at that time, the legal definition of cocaine was an extract of the coca plant. The coca plant only produces a single enantiomer, and so the suspect's lawyer argued that this substance, this white powder, could not have come from the coca plant. It was in fact synthesized. Okay, I'm going to move on to the next chapter. right, so this will be chapter 6. Okay, so we'll be looking at alkyl halides and their characteristic reactions, substitution and elimination. Okay, in the opening slide here, we have an example of a naturally occurring organic halide. This contains both a chlorine and a bromine, and this is found in a type of snail. Okay, these are three broad categories of alkyl halides, or halides, I should say. We have alkyl halides, in which which we have a saturated alkyl group. We have vinyl halides, okay, in which the halogen is bonded to an sp2 carbon, and then we have aryl halides. The reactions of aryl halides will be, for the most part, very different from those of alkyl halides. Okay, the halogens are electronegative elements. They're all more electronegative than carbon. The carbon-halogen bond is polar, so that carbon has a partial positive charge. Okay, so here we have an electron paramagnetic map of chloromethane. And around the chlorine, especially around the lone pairs, there's a high electron density, whereas on the other side of the molecule, where it's color-coded in blue, we have a low electron density. And this is critical to the reaction of alkyl halides. Okay, in substitution reactions, carbon then gets attacked by nucleophiles. Okay, substances that are electron-rich, electron donors, they're going to attack the carbon since it's electron poor. And we'll look at reactions where the halogen can leave, taking this pair of electrons with it. And when it does that, it becomes a halide ion. Okay, so we'll look at IUPAC nomenclature of alkyl halides or haloalkanes. Halogens are pretty low on the priority list. They're down there with alkyl groups. We'll be talking about other functional groups such as alcohols and alkenes and so on, which have a higher priority. Okay, so here we have 2-chlorobutane, and we want to use the lowest possible number. This is an example of a complex substituent on the right. This is 4, and then the substituent is 2-fluoroethyl. We start counting from where it's connected to the parent. So this is position 1, this is position 2. Okay, notice a couple things about fluorine. Fluorine is the only one of the halogens which has a one-letter symbol. Do not use Fl to designate fluorine. There's actually another element which has the symbol Fl. It was a recently discovered element. It's an unstable radioactive substance. It's element number 114 called fluvonium, and it has the symbol Fl. All right, notice the spelling of fluoro. It's F-L-U-O-R-O. Okay, so remember, you owe it to yourself to spell fluoro correctly. Okay, here are some other examples. We alphabetize, so 6-bromo-2-methyl-nonane. And then this one down here is cis 1-bromo-3-fluorocyclohexane. Okay, we assign the bromo as number 1 because it comes first in the alphabet. Many of these smaller alkyl halides are known by common names. This first one is also known as isobutyl bromide. In the IUPAC, it would be 1-bromo-2-methyl-propane. Okay, here we have sec-butyl bromide, which would be 2-bromo-butane. We have tert-butyl bromide, or 2-bromo-2-methyl-propane. But many of these are widely known commercially by their common names. Okay, here are some other common names. We've just recently used one of these, and that was methylene chloride, CH572. The systematic name is dichloromethane. CHX3 is a haloform, so CHCl3 is commonly known as chloroform, and that's in the United States, that is what it's known as commercially, chloroform. And then CX4 is carbon tetrachloride or carbon tetrabromide or whatever the halogen happens to be. Okay, so methylene chloride, CH2Cl2, chloroform, carbon tetrachloride, these are some common halogenated solvents. Okay, it's important to be able to classify alkyl halides because this allows us to predict their reactivity. Okay, methyl halides are those that have a halogen attached to a methyl group. Primary alkyl halide is one in which the halogen is bonded to a carbon that's attached to only one other carbon directly. And a secondary alkyl halide is one in which the carbon has a halogen and the carbon is bonded directly to two other carbons. Okay, so if we back up here, isobutyl bromide would be an example of a primary. Sec-butyl would be an example of a secondary, and tert-butyl would be an example of a tertiary. Okay, and here that is summarized. The R groups don't all have to be the same. Okay, here are a couple of common types of dihalides. If the two halogens occur on the same carbon, that is called a geminal dihalide. From Gemini, meaning twins. And then if they're on adjacent carbons, that is a vicinal dihalide. Okay, we've seen a couple of uses of alkyl halides already as solvents. Some other uses. Chloroform was once used as a general anesthetic, but it's not used for that purpose anymore since it is toxic and carcinogenic. Here's one that is used by inhalation. It's called halothane. Freons are used as refrigerants and foaming agents. The downside, though, is they can harm the ozone layer. So they've, in many cases, been replaced by low boiling hydrocarbons or carbon dioxide. Pesticides such as DDT, okay, which contains chlorine, are extremely toxic to insects. Not as toxic to mammals, but they do persist in the environment, and they do undergo biomagnification, so that predators at the top of the food chain tend to have high accumulations of these pesticides, such as DDT. And so the use of DDT has been very heavily restricted. Okay, alkyl halides have dipole moments due to the electronegativity of the halogen, and the order of electronegativity decreases as we go down the column. So fluorine is the most electronegative, followed by chlorine, then bromine, then iodine. As we go down the column, the bond length between the carbon and the halogen increases. Okay, notice that here, carbon-chlorine bond is actually a little bit more polar than a carbon-fluorine bond. Okay, the dipole depends not only on the difference in electronegativity, but also the distance between the two atoms that are bonded. It's because the chlorine to carbon bond is a little bit longer. That contributes to a larger dipole moment. Molecular dipoles depend on the geometry of the molecule. Okay, so they can reinforce each other, or they can cancel each other out. For example, in carbon tetrachloride, we have 4 highly polar CCl bonds, but they all cancel each other out, as shown here. So the molecular dipole moment is 0. Okay, because alkyl halides have these polar bonds, the dipole-dipole attractions are an important intermolecular force, but dipole-dipole attractions are not significantly different for different halides. London dispersion forces are going to be greater for larger atoms, okay, such as bromides and iodides, and mass will contribute greatly to the boiling point. So the greater the mass, the higher the boiling point. Okay, we said earlier in the semester that branching contributes to a lower boiling point, and so a more spherical shape will decrease the boiling point. Okay, so here we have 2 compounds with the same molecular formula, terbutyl bromide and N-butyl bromide. The straight chain alkyl bromide, you can see, has the higher boiling point. Okay, what about densities? Alkyl fluorides and alkyl chlorides with just 1 chlorine atom are less dense than water. But alkyl chlorides that have 2 or more chlorines are going to be more dense than water. Okay, and of course we saw that in the extraction lab. Okay, when we put dichloromethane and our aqueous solution into the separatory funnel, dichloromethane sank to the bottom. Alkyl bromides and iodides are all heavier than water, or they're all denser than water. Okay, so how do we prepare alkyl halides? Okay, we talked a little bit about that in chapter 4. We could use a free radical halogenation. Okay, that's not always the best way, but it is one way. Chlorination frequently produces a mixture of products. This is not a good lab synthesis, except when we have all of our carbons, or all of our hydrogens are equivalent. Okay, so for example, here we have cyclohexane, and it doesn't matter where we put that chlorine. It's going to be the same thing. And we should be able to separate chlorocyclohexane from the various dichlorocyclohexanes in case this gets chlorinated twice. Okay, on the other hand, if we have instead of cyclohexane, we have hexane. Okay, the problem here is that we can get one chlorohexane, we can get 2 chlorohexane, we can get 3 chlorohexane. We'll get a mixture of all of these. And if 1 chlorohexane was a product we want, that's going to be a minor product because it's a primary halide, and it would result from a primary free radical. So this is not a good plan for making, say, something like 1 chlorohexane. If you have a tertiary hydrogen, generally bromination would be a good synthesis. You can get selective yields, you can get good yields of the tertiary product. Chlorination, of course, is not very selective, but bromination is highly selective. Okay, next we'll look at allylic bromination. Okay, the allylic hydrogens are those that are 1 carbon away from an alkene. And if we do a bromination, the major product is going to be this 3-bromocyclohexene. Okay, the double bond takes priority, so it's between 1 and 2, so that's why the bromine's on 3. Okay, so these are the allylic positions that are circled right here. And the reason that the allylic position is favored is resonance. Okay, so we form bromine free radical, and it abstracts a hydrogen to give us HBr. That's a propagation step. This free radical now is stabilized by resonance. So the allylic radical is especially stable. And we have another propagation step here in which we produce the allylic bromide. Okay, this is a special reagent that is used specifically for allylic bromination. It's called N-bromo-6-enamide. The capital N indicates that the bromine is on the nitrogen. It's located on the nitrogen. Okay, the advantage to this is that it keeps the concentration of bromine molecules low. And as we'll see in the reactions of alkenes when we come to that, Br2 can actually add to the double bond. It's a competing reaction. But if we just want to carry out allylic bromination, this is a good reagent for doing that. It's highly selective, and it gives good yield for the allylic product. Okay, in this case, because of delocalization of the free radical, we're going to end up with two different products. Okay, the two resonance forms are not equivalent. Okay, so in the termination step, we're going to get two different products. Okay, the main focus of this chapter will be on two categories of mechanisms. One is nucleophilic substitution, and the other one is elimination. Okay, in a substitution, okay, we have some electron-rich reagent. Okay, it usually has a negative charge, but it could also be neutral. And it replaces the halogen. Okay, there's no change in bond order. Okay, so it substitutes. Notice what happens in elimination. We remove the halogen, but we also remove a hydrogen from an adjacent carbon. This is what we call a beta hydrogen. And we end up with an alkene. Okay, we'll look at two categories of substitution. First one we'll look at is the SN2. And the lab that you're going to be doing next Thursday is an example of an SN2 reaction. Okay, so the different parts of the reaction consists of the alkyl halide, what we call the substrate. That's what gets attacked. In the case of our reaction we're doing next week, the substrate's actually going to be an alcohol. And then you have a nucleophile. That's what does the attacking. And here we have a species that has a lone pair and a negative charge, hydroxide. And that is going to replace the iodide. So our product here is methanol and alcohol. And then our byproduct, which is iodide, this is called the leaving group. Okay, so nucleophile, substrate, iodide is the leaving group, and then methanol is our product. Okay, so as you might guess, S stands for substitution, N stands for nucleophilic. The 2 stands for bimolecular. This has a bimolecular transition state. Okay, so this is how the reaction occurs. Okay, so here we have iodomethane. It's a polar molecule. The carbon side is electron deficient, so it's going to attract electrons from the OH minus. And this bond forms and this bond breaks at the same time. And so the transition state would look something like this. Okay, it's bimolecular. One bond is forming, one bond is breaking at the same time. And then we go on to products. Okay, it turns out that not only is this bimolecular, and because it's bimolecular, it is also a second order kinetic reaction. So the rate law depends both on the nucleophile and the substrate concentration. It's first order in both of those, second order overall. And this is what's generally called a concerted reaction, where bonds are forming and breaking at the same time. Okay, so there's just one step. There's no intermediate. There's the reactant energy level, activation energy, transition state, and products. And in this particular case, the reaction is exothermic, since the product energy is lower than that of the reactant energy. SN2 reactions are very useful. This is just a partial listing. We can make so many different functional groups, starting with alkyl halides. We can make other alkyl halides, for example, alkyl iodides. We can make alcohols, ethers, thiols, thioethers, amine salts, azides. We can make longer chain alkynes. We can make nitriles, esters, phosphonium salts. Okay, those reactions will all follow the same pattern as the reaction of iodomethane with hydroxide. Okay, well, not all nucleophiles are the same, not all substrates are the same, and the rate of reaction as well as the type of reaction are going to depend on the nucleophile, the substrate, the leaving group, and as we'll see in some cases, the solvent. Okay, so these are some common nucleophiles. And down here on the left-hand side, we have the weak nucleophiles. Okay, neutral molecules such as alcohols and water, carboxylic acids. Okay, fluoride is actually a weak nucleophile. We have the moderate ones, and then we have the stronger nucleophiles. Okay, notice the stronger ones all have a negative charge. I guess except for, well, the phosphine doesn't. Well, most of them have a negative charge. Okay, so what do we mean by nucleophilic strength? Nucleophilicity and basicity are not exactly the same thing. Nucleophilicity actually is a kinetic concept. It refers to the rate of attacking a carbon. Okay, so stronger nucleophiles will attack faster. Basicity is an equilibrium concept. Often, strong bases are also strong nucleophiles. There are a few exceptions. Okay, so these are some trends in nucleophilicity or nucleophilic strength. Okay, first of all, a negatively charged nucleophile is going to be stronger than its neutral counterpart or its conjugate acid. Okay, so OH minus is a strong nucleophile. Water is a weak nucleophile. The conjugate base of hydrogen sulfide is stronger than hydrogen sulfide. NH2 minus is a very strong nucleophile, much stronger than ammonia. Okay, there are some periodic trends. For example, as we go down a column, the nucleophilic strength actually goes up. So in the series of halide ions, iodide is the best nucleophile, fluoride is the weakest. Okay, this is the column right next to the halides. The SEH minus ion is stronger than the SH minus, which is stronger than the OH minus. Okay, and then going over one more column, triethylphosphine is stronger as a nucleophile than triethylamine. Okay, so a larger atom is more polarizable. The electron cloud is more fluid. As we go across a row of the periodic table, if we compare similarly charged series, NH2 minus is a stronger nucleophile than OH minus, which is stronger than F minus. Ammonia is more nucleophilic than water. Phosphorus and sulfur are right next to each other in the periodic table. Phosphorus comes before sulfur. Okay, so this is more nucleophilic than the triethyl, or the diethyl sulfide, I should say. Okay, so if we have a small, highly charged atom, such as a fluoride, this is referred to as a hard nucleophile. It's small in size, the charge is very concentrated, and in the transition state, when it attacks, there's not a lot of bonding. Iodide, on the other hand, is much more polarizable. The electron cloud, as I said, was more fluid, and because of its larger size and its greater polarization, there is more bonding between iodine and carbon in the transition state. So the bigger atoms have a soft shell or electron cloud that can start to overlap the carbon atom from a farther distance. Solvent can have an effect on the rate of SN2 reactions. Water and alcohols are examples of what are called protic solvents. Protic solvents are those that are hydrogen bond donors and acceptors. And if this reaction is carried out in a solvent of some alcohol, ROH, maybe ethanol or methanol. Okay, notice that the fluoride ion is tightly bound by the solvent. And so it has to shake loose those solvent molecules before it can attack the carbon. Polar protic solvents will have acidic hydrogens, either OH or NH, that can solvate the nucleophile, which reduces the nucleophilicity. Nucleophilicity in protic solvents increases as the size of the atom increases. Okay, so that means that if we substituted iodide for fluoride, there would be a lot weaker solvation. And so the iodide is much more free to attack the carbon. Okay, one of the ways that you can avoid the effect of solvation is to use a polar aprotic solvent. Polar aprotic solvents do not have acidic hydrogens and therefore cannot hydrogen bond. They can accept hydrogen bonds, but they can't donate hydrogen bonds. These are some examples of aprotic solvents. This one is acetonitrile. We have in the middle dimethylformamide, or DMF, and then acetone. And then there's some others that are listed here. DMSO, dimethyl sulfoxide. Dimethyl sulfoxide looks a lot like acetone, except this middle carbon is replaced by a sulfur. Okay, and then because polar aprotic solvents will solvate cations, but not anions, SN2 reactions are going to proceed much faster, very significantly faster in some cases in aprotic solvents. Okay, an alternative to using polar aprotic solvents is to use crown ethers. Okay, this compound is called 18 crown 6, and it's called a crown ether because in 3 dimensions it looks like a crown, it's shaped like a crown. And in acetonitrile, okay, they're using both a crown ether and an aprotic solvent. The crown complexes the potassium ion. Okay, so there's a hole in the middle. It's just not only like a crown, but it's like a donut. And the hole in the middle is just the right size for a potassium ion to fit snugly. And so it ties up the potassium ion, and then the fluoride ion then is free to move around and becomes much more nucleophilic. Okay, there are some other crown ethers. This one is 18 crown 6. Okay, what that means is an 18-membered ring, and then the 6 refers to the 6 oxygens. 15 crown 5 also has a hole in the middle. That hole is too small for potassium, but it will fit a sodium ion snugly. Crown ethers, such as 18 crown 6, can be used to dissolve compounds such as potassium permanganate, KMnO4, in organic solvents. Okay, we've talked several times about how like dissolves like. Potassium permanganate, KMnO4, is an ionic compound. It is not going to dissolve in organic solvents, and a lot of the reactions we want to do in organic solvents. But if we add 18 crown 6, that ties up the potassium, and it surrounds it with this hydrophobic outer layer, which then dissolves. And then the anion goes along with the cation. There's a compound called purple benzene where you add 18 crown 6 and potassium permanganate to benzene. Okay, normally KMnO4 would not dissolve. So fluoride in this example becomes a good nucleophile. Many other anions become good nucleophiles. Okay, we're out of time, so next time we'll talk about how choice of leaving group can affect the rate of the reaction. Okay, so that is all for today.